Hello, everyone. It's everything working right? It's everything okay now? So, welcome for more one day of the Água, NAP Água's event, Água que nos conecta. Today, we'll be receiving Professor Matt Curl from Griffith University. And we're gonna start the talk with in English. But whatever you guys need to have some questions in the end, you can talk, you can speak, write in Portuguese or English. So our team will translate to the guest, to the invited guest. So I think it's everything work finally. If there is any question, we can start right now. My name is Tatiana, and whatever you guys need something, you can ask direct for me or for our team. So I think we can share Professor's screen. So the room is yours, Professor. Whatever you need, you can ask for us. You can ask for help if you need.
Thank you so much. Yeah, so I'm really grateful to have this opportunity today. Thank you for the invitation. I'm very honored to be presenting here at this event. Many thanks to the TWRA for their collaboration and their support. It's through the TWRA that I've gotten to know Professor Yara and others in the group here. And I think we have a really fantastic relationship with the Australian Rivers Institute, which is where I'm based in Griffith University. So I wanted to just pick up on the topic area of connected waters. I think it's a wonderful way to look at the research that we're doing and to look at the world and the waters that support people and the environment and our cultures. We all know that the water is connected throughout different parts of the hydrological cycle. In fact, we learn this as kids in school. You know, my kids at the moment are learning about the hydrological cycle. They're very young. They're only, 6 or 7 years old. And they're already gaining this understanding that the water that flows around our planet is all connected. And we need to be careful to understand what those connections are and how we can make sure we maintain our waters as safe, sustainable, high quality supplies for everyone and everything that needs that water. So yes, as I mentioned, I'm based in the Australian Rivers Institute as well as the School of Engineering at Griffith University. Part of the Australian Rivers Institute's mission is to try and help to contribute to solving some of these grand challenges that we have for water around the world. First of all, obviously trying to balance the water need for people, for our cities and our farms and our communities with the needs of our ecosystems that are also very much dependent on these waters. Trying to, deal with the issue of biodiversity declines in many areas of the world. I think that's probably common across much of the world. There are areas where, our biodiversity is declining and water is a key part of that. Tackling pollution, so looking at, the excess nutrients, the emerging contaminants, all of the water quality threats, sediment, organic and inorganic pollutants that are a threat to the quality of our water supplies. And then the big question of climate change. How do we make our catchments, including the underground waters, more resilient to this changing climate that we have? It's still hard to predict what is the full impact when it comes to water from climate change, and we're still adapting and needing to adapt very quickly to changes that are happening in the hydrological cycle worldwide. So where do I fit in with all this? I am a hydrogeologist, so I trained in the earth sciences, and my work is all about trying to understand what's going on below the surface of the earth and understand the waters that are flowing beneath our feet. So I always try and show little diagrams like this to make people understand that, even though we only see this much water when we're looking at the surface of a landscape, there's actually a huge amount of water sitting beneath us that we can't see. And it's that water which I focus mostly on in my work. But I also am very careful to make sure that when I look at the water that's underground, I'm also thinking very carefully about how that water is connected with the surface systems that we, are working with and interacting with our human and ecological communities. So I work a lot on springs. Last year, I published a book through Wiley and the American Geophysical Union about the threats that our springs are facing in a changing world. And this is just a picture here of one of the many springs that I've been studying and researching. Springs are incredibly important places throughout the world. The technical definition is that a spring is where underground water makes its way to the surface and starts to flow out into the landscape. A lot of our river systems, a lot of our catchments, the starting point is the springs. The springs are the thing that start at the top of the catchment, and that's what keeps our rivers flowing when there's no other rainfall, no other runoff sustaining them during droughts. The springs are places of cultural significance. Many Indigenous cultures around the world have always found springs to be important places. There are many different terms in different languages about springs being the birthplace for water and the birthplace for life as well. Some cultures see springs as the eye to the underground. It's like an insight into what's happening below. So many stories about peering into the spring and seeing what's going on or predicting into the future. These are all parts of many cultures and stories. So springs are incredibly important places worldwide. And I think we need to make a lot of effort to try and protect and preserve them. I'll play just a video of what this spring looks like when it's flowing, just to demonstrate the connection. This is directly where the connection between the underground water and the surface water happens. It's the interface between those two different places. So we see this beautiful pool of water, and where is that water coming from? It's leaking out directly from the rocks. So in this case, we have a sandstone aquifer. The water is directly just flowing out from the rock between cracks in the rock. And that's what produces these beautiful pools, which is then, this one's called turtle pool, because the turtles really need this pool. It's where they do their breeding. And it's actually what we call the headwaters. It's the top part of this catchment. So there's a major river, which is called the Dawson River in English. It's also called the Wurundjeri River in the Indigenous language for this area. And the health of that river depends upon these springs, because this is the starting point for that river, for these waters. So I think, it's a really important area of research. And I'm going to talk to you now about a few case studies, types of work that I'm involved with, where, we're trying to understand underground water and why it's important. Okay, so just quickly a note on groundwater at a global scale. There's a lot of work that's been happening recently, a lot of papers published in Nature about what we call the planetary boundaries. So, humanity is having a huge impact on the biosphere. It's influencing the climate. It's changing the nitrogen and carbon cycles, major impacts on freshwater. And so at a global level, it's really important to understand how freshwater usage is coming up against that boundary of what's sustainable use and what's going to be handed on to future generations. So here's just a picture showing what it looks like when a landscape is changed by the use of groundwater, underground water. All of these little circles in the green that are up on screen are actually massive scale irrigation systems with a center pivot. And so there's a pump that comes up and basically irrigates in a big circle. And in the middle is where the groundwater is coming up from under the ground. So this is in Oklahoma in the US. It's an aquifer called the High Plains Aquifer, which is facing issues with groundwater depletion because the rate of extraction is far, far exceeding the rate of natural replenishment of the water under the ground. This is a picture of a catchment which is flowing out into the ocean and carrying with it tons of sediment and tons of nutrients from the farming. This is another really major part of the planetary boundary that affects freshwater, is all of the flows of nitrogen and phosphorus that are coming from the catchment, making their way into these coastal ecosystems and putting them out of balance. And so groundwater is actually a big part of this picture as well. Recently, my colleagues in Australia did some quantification of how much of the nutrients that are making their way to the coast is actually coming from the underground water. It's harder to see. We don't notice it. Everyone's focusing on what's going on, the runoff from the farms at the surface, but actually the load that's coming from underground is very significant contribution to the nutrient load in our estuaries. So again, we need to think about what's going on underneath and how that connects with the surface if we're really going to understand our water systems and the threats that they face. I work with isotope tracers. So they are naturally occurring elements that are in the water. And I do a lot of work just analysing these isotopes to see what we can learn about where water is coming from, how long it is spending under the ground, what type of geological material that water is coming into contact with, and where contaminants might be coming from. And so the ultimate aim of my research is to try and protect groundwater and connected springs and streams and wetlands from degradation, informing sustainable management for future generations, because it's all about handing over the planet in a condition that's as good or better than we experience to our future generations. The thing about groundwater is it moves very slowly compared to surface water. So a lot of times people are very surprised to learn that the water that's moving underground is taking many years, sometimes hundreds or thousands of years to just go quite a short distance. So that creates a bit of a problem or an issue that we need to be careful when we're thinking about managing. Groundwater is very easy to contaminate. We can get pollutants and make them enter the groundwater really easily if we're not careful. But it's very hard to restore because you can't just flush the contaminants through in one day or 1 week or 1 year. The contaminants, once they're there, will take a long time to make their way through the system. And so this is some good work by my colleague, Scott Jasechko, which shows that in our global aquifers, we have a lot of what we call fossil groundwater. That's groundwater that was recharged. It went under the ground tens of thousands of years before the present time. So it's very old, it's very slow moving. But at the same time, that water is very vulnerable to what's happening in modern times without contamination. So again, easy to contaminate, hard to fix, slow moving systems. So this is the mentality we need to have when we think about underground water and its protection. The type of work I do is like, sampling groundwaters and measuring isotopes, things like carbon-14, things like chlorine-36, which tell us about how long the water takes to flow from one place to another. Isotopes of strontium to work out like what rocks the groundwater has been interacting with before it makes its way to the surface. And we produce these kinds of maps and charts. I do a lot of field work. This is me out in the field collecting water samples. So I get to have a lot of fun doing field work. And then I do a whole lot of lab work. So this is a, accelerator mass spectrometer in ANSTO, which is where we do all the analysis of isotopes in the lab. So I think, there's a window of opportunity that we have for groundwater scientists to be informing good decisions about sustainable management of our freshwaters on Earth. And this is really important for Earth's future. I'm going to talk in a moment about some work I did a couple of years back, which is still going, about mining impacts from Australia's biggest coal mine, and some springs that we've been researching that are quite close to the coal mine, and the real important job that we have to try and protect the springs from any impact from the mining, and do it quickly, because once those springs are gone, they're gone. And this is, again, further work recently just published in Nature late last year, which is about the rapid decline in groundwater storage within many aquifers globally. So again, looking at some of the global data sets, we see a picture where there are a lot of places in our world where the rates of groundwater extraction are too high, and it means that the levels are declining over time. Okay, case study 1. I want to talk about groundwater quality here. And this is some work that I was involved with for about 5 years. I worked with my previous university, RMIT, and many water corporations based in Australia in different regions. And I had many colleagues and co-authors in this work. We worked with analytical chemists and isotope scientists and water industry people. And it's all about trying to work out what are the ways we can identify contaminants that are coming from our wastewater treatment plants into the groundwater, and how can we distinguish that contamination from other sources of contamination in the same catchment. So in many areas of the world, we have what we call these peri-urban areas. It's like on the outside of our cities. Our cities keep growing and they keep using more land. And on the edge of our cities, we have this crossover between often agricultural land and the urban land. And we have in these areas many different ways that groundwater can become contaminated. It includes agriculture, it includes landfills, it includes wastewater treatment plants. So if we want to do a good job of preventing contamination and cleaning up contaminants, we need to be able to distinguish between different contributions, different contamination sources. This is really hard to do with normal groundwater quality sampling. When we sample things like nutrients in groundwater, like nitrate and ammonia and phosphorus, we just get the concentration. It doesn't tell us, just by analysing the concentration, where that nitrate comes from and what proportion comes from source of contamination A or source of contamination B, right? So our job was to try using different contaminant traces to understand what component, what amount of contamination comes from the different sources of contamination in the catchment. And we're using contaminants of emerging concern, trace organic contaminants that are present in very low concentrations, but which we can now analyse to use as basically like a detective tool, a forensic tool, just like what a murder cop would do on a TV show. He's trying to find the evidence of who's responsible, who did it, and he uses a sensitive tracer. Okay, and we did that work to combine contaminants of emerging concern with environmental isotopes to get a bigger picture of what's going on in the groundwater. So we know that there's a huge range of organic compounds that get released into the global environment because of the global chemical industry. There are many, many things, drugs, insecticides and herbicides, industrial chemicals, things like PFAS that people all know about. So these synthetic chemicals that humanity produces that then get released into the environment. So we can actually use these traces because they are quite diagnostic or quite distinctive for different sources of contaminants in the environment, right? So only particular industries are using certain chemicals. Only agriculture is generally going to be using things like insecticides and herbicides. Wastewater treatment plants have certain technologies that treat many of these contaminants, but they will leave behind certain organic contaminants that are very persistent and they can't be removed by wastewater treatment. So we can pick them out and say, this must be a chemical that's coming from the wastewater treatment plant. So this is the work we did, mapping contaminants of emerging concern and using that as a new way of tracing different contamination sources in a peri-urban area. The key thing about using these contaminants, so there are thousands and thousands of organic contaminants. What we need are contaminants that are very persistent, because if they degrade in the environment, we can't find them. So we need to look at the persistent organic pollutants and then try and work out where these different pollutants are coming from different sources in the catchment. Here's a bit of an overview, a case study. So we had this catchment here, and what I'm showing here is just a heat map for nitrate nutrient pollution in the groundwater. And you can see that there's a lot of pollution over here. There's further pollutants over here, and then an area that's not been impacted yet by the contamination. There's agriculture in the catchment. There's old landfills. There's a golf course, and there's a wastewater treatment plant. And the question is how much of the nutrients are coming from the different sources. So firstly, we're using radiogenic isotope traces. And basically what we find is trying to work out how old the water is, how long it's been under the ground. Now, in this case, when we take a transect of samples across a wastewater treatment plant, we can see that when we take groundwater samples right near the treatment plant, there's very young water that looks like it's only recently got into the ground, which tells us that there must be an active leak of water into the groundwater system because it's very young water. And then we see this kind of exponential decay as we sample along the flow path. So we see that there's this water that's entering at the wastewater treatment plant, and then that water is flowing in this direction towards these wetlands here, and gradually it's getting older as it moves along the flow path. So this is an alarm bell that tells us there's a problem because we have a leak at the lagoon, and we identify that using the radioisotopes. Next, we use the contaminants of emerging concern. And in this case, we use a drug called carbamazepine, which is very widely used around the world and very persistent. So even when it goes through a wastewater treatment plant, it can't be removed, it can't be treated. So it remains in the waste that comes from the treatment plant. And if that is what's contaminating the groundwater, you will find carbamazepine as a marker of that contamination in the water. At the same time, we can sample simazine, which is a pesticide that's used by the farmers and generally not so much associated with the wastewater treatment plant. So if we plot the ratio of those two compounds, the drug divided by the pesticide, we get an index which says this is very much the higher values are to do with the wastewater treatment plant, the lower values are to do with the agriculture, and we can separate the different sources of contamination in the catchment. It's a good technique. And then we can also start to look at how long the contamination has been going on for. Is it short term? Is it long term? Is it 10 years? Is it 6 months? Is it 20 years? And we can start to build a timeline. So we published this work in a series of papers, and there's a little bit of information online. We worked with ANSTO, and they published a story about this, which I'm sure you can find in the online world. And we found it really important work to help with trying to manage contamination in these peri-urban areas. So that's my first case study. I want to move on to a second case study, a little bit different. In this work, this project, we're trying to use environmental traces, so again, the isotopes that I mentioned earlier in groundwater, to really understand what are the sources of water that are contributing to springs in a place called the Great Artesian Basin in Queensland. The Great Artesian Basin is actually one of the largest groundwater systems in the world. It underlies about 20% of Australia's whole land mass. There's only a couple of aquifers in the world that are bigger in scale. And it has these springs, which are basically the last place in the catchment where the groundwater makes its way to the surface. So they're really important. A lot of the groundwater in these springs is very old, as you will see. It takes many, many thousands of years to get to the spring from the point it starts in the aquifer. And so in this case, we did some work with Coast and Country, which is an environmental organisation supporting the work through an Australian Government Research Council grant. And my colleagues based at Flinders University, Monash, UQ and La Trobe universities. So the focus of this research is that we know that the water from aquifers, the underground water, is what keeps our rivers and our wetlands wet and flowing during periods of low rainfall. Aquifers in this basin, Great Artesian Basin, are the source of water for many springs, including famous mound springs. They support endemic ecosystems, endemic meaning that they don't occur anywhere else in the world. You'll only find these plants and animals in that particular spring. And they have huge cultural significance to our Aboriginal and Torres Strait Islander people here in Australia. The last couple of decades, there's also been a boom in mining development in the Great Artesian Basin because there are coal and oil and gas resources in the basin that companies want to try and extract. So what are the long-term impacts of these mining projects on groundwater and their connected surface flows and ecosystems? That's the focus of this research. And what does this mean for hydrological, cultural, and ecological values? Okay, the case study we'll talk about. This is central Queensland in Australia, in the northern part of Australia. And this area is the Carmichael River catchment and the Dungabulla Springs. So all of those orange dots there on the map are different spring vents where groundwater is coming up to the surface and creating a little wetland. This area in black is an approved coal mine that the Australian government approved 4 or 5 years ago, and it's the largest approved coal mine in Australia. This image here shows from a drone footage what the springs or what some of the springs look like. So you can see, you have these areas where there's permanent water in the landscape, these pools where the groundwater is sustaining the vegetation and keeping the landscape wet. I want to try and play a video just to show you a flyover of what they look like, these springs. Again, this is some drone footage collected by a colleague just to show the importance of these springs for the landscape, the permanent water that they provide. So you can see open water here in this dry catchment. And then over here, in this part of the system here, that's actually what we call a mound spring. There's an elevated area with some vegetation that's built up because it's had access to permanent water. And these are actually swamp paperbark trees. So they're normally associated with coastal areas with a wet climate. And the reason they're able to still survive in this area is because there's always been permanent flow of fresh water to the spring in this case. So very beautiful places, very important culturally and ecologically. To the Aboriginal people of this area, the Wangan-Yagalingu people, they believe that the springs are the starting point of our life, and they're also part of their dreaming stories. They're very concerned that the coal mine is going to devastate the Dungabulla Springs, and if their land and waters are destroyed, their culture will be lost, according to them. So their grandchildren and their children won't know their culture or who they are properly without these springs being there. And that's a submission they made to the United Nations in 2015, trying to stop the coal mine from going ahead. That was unsuccessful. Here's a picture of what the area looks like now. So the coal mine was approved 4 years ago. Now this is what it looks like on a satellite image. The mine is at the moment actually quite small compared to the final mine plan. So they've so far been digging one coal pit. They plan to have a whole series of pits, I think something like 6 or 7 different coal pits in the whole area. So this is just 3 years worth of mining at the site. In order to do that mining, they have to pump lots of groundwater out of the system because they can't have groundwater inflow into the mine workings. That's a health and safety issue, and it floods out the coal. So they also pump a lot of groundwater to dewater the site. This area here is where the Dungabulla Springs are. So you can see some of the green areas, some of these wetlands where we've got permanent water in the landscape. That's where the springs are, and they're providing a lot of the flow that goes to this river, the Carmichael River, which flows right by the mine site. So we did some work sampling these springs, and we have been collecting water samples from the spring wetlands and trying to get the isotope analysis to understand how vulnerable these springs are to the impact from this coal mine that's right near them. We use a combination of techniques. We use environmental isotopes, we use geology and geophysics to better understand the sources of groundwater that sustain those springs. We do a little bit of modelling. So some of the isotope work, we use what we call a lumped parameter model with the tracers to identify how old the water is and how much mixing there is between, say, younger water and older water. And then we're also looking closely at the data that's being reported by the mining company. They have to monitor groundwater levels and quality. And so we take that data and we interpret that and try and understand what it means for changes in the groundwater system. That, again, it's great, interesting work. We get to go out in the field and collect the water samples from these kinds of bores and springs as well, and then analyse it. Ansto, our project collaborator, as well. A few results. So this is some analysis of one isotope that we analysed called strontium 8786, so it's a radiogenic isotope. And you can see that depending upon where we are in the catchment with different springs, we have different values of strontium isotopes in the water that we sample. And there's quite a clear difference. There seems to be higher values in this area, this cluster over here, much lower values along the river itself over here. And this is closer to the mine. So that mine site's just up in this corner over here. When we put that data into box plots, we can see that the springs, again, have these two clusters. So these are the western springs over here, these ones on this side. This little cluster is the eastern springs over here near the river. And then we have the composition of the groundwater that we sample from different aquifers that are in this geological system. And you can see that there's a better match between the springs and some aquifers compared to others. So we see that the springs have a different value to local rainfall. So it's not the nearby rainfall that's sustaining the springs, it's the groundwater. And we see that there are certain aquifers, so this one here, Clematis aquifer, the Dunder beds, which overlap quite nicely with the spring composition, which tells us that probably most of the water in the springs is coming from these particular geological layers, which have groundwater stored within them. We also have rock samples, so these box plots here is like, what is the strontium isotope ratio actually in the rock? So when the water interacts with the rock and dissolves the rock while it's flowing through, it will pick up the strontium that's there in the rock and reflect that when it flows through the aquifer to the spring. So a very useful technique for identifying which rock units spring water is actually coming from. Now we're looking at the radioisotope results. And basically the way radioisotopes work is that when water is rainfall in the atmosphere, it will have a certain amount or certain concentration of a radioisotope. But when that water goes under the ground, it will start to decay according to the half-life of the isotope. And the longer it spends under the ground, the less and less of the radioisotope is left in the water sample. So we can pick out what modern water looks like, very young water that's like, current day rainfall. And we can plot that on a chart like this. So this is like what modern water will look like. And then we can plot our spring samples and our groundwater bore samples to see how close to the modern composition is this water. And what we see is that some of the springs, they have age values that are kind of close, relatively young, close to modern. But then we have other springs down here which plot nowhere near the modern signature. And in fact, the ages are at least 50,000 years. And when we start to look at chlorine-36, which is this isotope here with a long half-life, some of the springs and the groundwaters have residence times, that means how long they've been under the ground, of 500,000 years, almost up to 1 million years. So that's very old groundwater. So what we see flowing up at the surface of the spring, the connection between that and the rainfall that happened yesterday is almost, it's nothing to do with it, right? So it's rainfall that fell 500,000 years ago and made its way slowly to that spring. So I think that's really important when we're thinking about, the time scale of something like a coal mine. It's going to be going for a few decades at most. This groundwater that sustains the spring has been there for 500,000 years. And so we can very quickly destroy a spring or, damage an aquifer that's been doing what it's doing for hundreds of thousands of years just through a big mining project that is really actually a short-term project when you think about it. Okay, we have, again, these two groups of springs. The western springs, which I showed earlier, a very old source of water, 500,000 years old. The eastern springs along the river, much younger. They contain water that's, much more modern. Now, it's actually these springs that are probably the most vulnerable to the impact from the mine because they're much closer. So these eastern springs here, they're getting their water from nearby, from recharge that's happening in this landscape up on the hill. And that water's flowing directly to the springs. Over here, we've got the coal mine, which is very close. And as soon as that coal mine starts to change the flow gradients and the water levels in the aquifer system, they can disrupt this flow path that's close to these springs and potentially damage those springs. So we're watching those springs really closely because we're very concerned that they're too close to the mine and they'll be impacted. These western springs, we think, might be getting water from further away to the west, a much longer flow path. So they're less vulnerable at the moment, but in the long term, there still could be a very significant impact. And remember that the age of that water is 500,000 years old. So if it gets destroyed, it's very hard to restore that. Okay, last case study I want to talk about now is about what we call managed aquifer recharge. So I also do work in the engineering field and trying to work out, can we find ways to use groundwater within the water cycle in a way that is sustainable for our urban communities. And so this is some work done with Melbourne Water. And what's happening in a lot of catchments worldwide is that the farmland is now being converted into urban land because population keeps growing and there's demand for, new housing estates and new urban areas all around our cities in the world. And so this is a picture, 2006, what the catchment we're looking at was looking like. You can see there's the edge of the city is up here, and then everything around here is farmland. Then we start to go 2010 and we see that there's new housing developments happening. 2015, there's more and more. And by 2017, we're really starting to see a lot of conversion of that agricultural land to urban land. So big change to the catchment, big change to the runoff and the hydrology. Also changes happening under the ground that you can't see. And our job was to try and understand what's going on. So before the urbanisation process took place here, we basically had a case where the water balance is relatively simple. We have rainfall, which infiltrates under the ground. We have extraction of groundwater, which is irrigating the crops and the farms. We have surface runoff, and we have groundwater, surface water interaction, and also some native vegetation that's remaining in the landscape. When that land is converted to urban land, things get much more complex. The urban hydrological cycle is a lot more complex because there's all these new sources, new infrastructure that changes things like runoff and evaporation. Water is being imported to that catchment from somewhere else, like from a surface water catchment for water supply. We have sewage networks and wastewater treatment plants that are taking water and treating it and releasing it to the environment. You have water-sensitive urban design infrastructure, so wetlands that are there designed to control flooding in these communities. So there's a lot more interactions to try and understand in the urban environment, and also a lot more from the water quality point of view, a lot more contaminants that can make their way into the groundwater, generally speaking. So we did some work trying to map where recharge is happening in this catchment, where it's changing from, you know, an agricultural land to an urban land. And so we were looking at profiles through the soil to work out where, you know, infiltration is happening in the catchment. And we were drilling our monitoring bores and trying to work out, you know, if we sample underground, can we see any indication of recharge happening? And what we started to find was that the infiltration of the rainfall or the surface water into groundwater was very, very restricted to some certain areas, because most of the time we have clays which are stopping the water from infiltrating underground, right? And so we started using tracer concentrations, so those isotopes, to basically identify the hotspots where we're getting the rainfall and the surface runoff really getting into the aquifer system. Okay, and we developed this new conceptual model of where the recharge could be happening based on the geology, based on the soil type. And we did some mapping of those radioisotope traces in some of the shallow groundwater to see, well, where do we see very modern, very recent infiltration to the groundwater, and what do we see elsewhere in the catchment? We were monitoring the groundwater levels and the groundwater conductivity to see if there are any spikes in the level associated with rainfall too. So, you know, the conceptual idea is that when it rains, if that water is infiltrating to groundwater, you'll quickly see a jump up in the groundwater level, and then gradually things will go back down. Generally, we might also expect to see the groundwater become more fresh when there's rainfall recharge, because the rainfall is nice and fresh and it freshens up the groundwater, so the EC should be going down. So we started looking at these hydrographs, which is helping us to identify where we've got active recharge going on. And then we started mapping out these tracer concentrations. So tritium is an indicator of very young groundwater recharge. Radiocarbon often tells us about older groundwater, but you can also identify modern recharge if you have values greater than 100. So 100% modern carbon indicates that you've got, like, rainfall that happened yesterday should have a value of that. So we found a hot zone where there's a lot of recharge happening, because we see the isotope traces, the tritium and the carbon-14, very elevated in concentration. But then elsewhere in the area, we really start to find there's not much, you know, the groundwater again is looking very old. There's no tritium or very little tritium present. And so we were able to focus in on the areas where we see more evidence of active recharge taking place. And we find actually in the areas where there's recharge going on, there's some protected land which is being used as a like botanical garden, which we found to be quite good news, because that's there's no farming there, there's no residential areas. It's actually just like a nature reserve, and it happens to be in the area where we found a lot of recharge happening. So one of the things that we decided, this is Ben, my PhD student doing this work, we really need to make sure this area of natural vegetation is protected, because that's where the recharge is getting in. And if we start allowing houses to be built and urban infrastructure, it's probably going to contaminate the groundwater. We also did some mapping on some quantification of recharge rates using a very simple technique called chloride mass balance, and come up with a recharge map that basically shows, again, this is the hot zone where we've got high rates of recharge. Elsewhere in the catchment, you have very low rates of groundwater recharge. So if we want to protect the recharge and the quality of the groundwater, we need to focus on protecting this region here. Again, we combine that method with water table fluctuation mapping, which shows when there's rainfall events, we do see increases in the groundwater level. It's very clear here. There was a big rainfall event just around Christmas 2016, and we saw the groundwater level rising. You can actually use that to estimate the quantity of the recharge in that point, and then again start to try and quantify how much infiltration is happening in that part of the catchment. And so that using different techniques to estimate recharge independently is a powerful way to make sure that your water balance is actually, is robust and it's reliable. This area, basically, we found that about half of the recharge is happening on about 15% of the land area. So really important findings. Last part of this research and the last part of my seminar is just talking about how these constructed wetlands, which are being basically built by the Water Authority in many of the new urban areas. And the idea is to try and prevent flooding, so all the stormwater can run off into these retarding basins, wetlands. What happens underneath these wetlands, though? Do we have any interaction with the groundwater? And so we did some sampling of groundwater before one of these things was built. Then we looked at what was happening after it was built, and then saw the change in the groundwater before and after this wetland was installed. So there's Ben going out to sample the wetland. He's actually looking a little bit unhappy there because it's a very cold morning in Melbourne, and he's wading into the wetland to get his logger. But it was very important research. And what we found was that basically when we had heavy rainfall events, we would see a really quick rise in the level of the wetland, and then also in the shallow groundwater, which is this blue line here. And at the same time, we would see the electrical conductivity of that shallow groundwater dropping really quickly. So it's indicating that you've got fresh rainfall infiltration very rapidly recharging underneath the wetland into the groundwater. And we were able to basically show that in the early phase of the wetland, there was some big highs and lows, and, very saline water and then very fresh water, and a lot of change happening. And then it transitioned to this new equilibrium where we had much fresher groundwater underneath the wetland, because the bubble of recharge from the wetland to the groundwater has been growing with time and replacing the old groundwater that was there. So basically, this is telling us that the wetlands are acting as little point sources of recharge of the stormwater into the aquifer. And that gives us the idea that if we're managing this catchment and trying to prevent groundwater depletion, we can actually be a bit clever and design these wetlands to recharge where we want the water to go into the aquifer, making sure that we, that water is high quality and it's not polluted. But it could be a good way to sort of build the resilience of that catchment. And we proved basically this mechanism by showing that, a lot of the tracer concentrations that I've mentioned before changed very dramatically between before the wetland and then after the wetland was completed. So basically a big hydrological change following the urbanization process. So, we're basically saying that the wetlands are acting as new source focused recharge, which can provide opportunities for improved urban water cycle management. But we must be careful to monitor the quality of that water, because we don't want to be infiltrating polluted groundwater into our aquifer systems. Okay, well, that's all I have time to talk about today. I'm really pleased to have this chance, as I say, and thank you to everyone for hosting this event. Again, there are my details up on screen if you'd like to reach out to myself or the Australian Rivers Institute. We're great partners with the TWRA, and we love interacting with what's going on in Brazil. So thank you again, and I'll open up for questions and comments from the audience.
Oh, thank you so much, Professor Math. We have one question from Professor Valeria. So the question is, thank you so much for this talk. It was awesome. Could you talk about the relationship between climate change and groundwater?
Wow.
That's
a big question. A big question. Okay. I'll try and keep it short. There's two ways that climate change can affect groundwater on planet Earth. First way is that the climate variables like the temperature and the evaporation and the transpiration and the rainfall rate are changing because of climate, right? That, in terms of the groundwater system, the main thing that will affect is the recharge rate, the infiltration. If we have more intense rainfall, we may actually get increases in groundwater recharge. If we have higher evapotranspiration rates, we're going to have less groundwater recharge, because the ET is actually the thing that really controls recharge in many areas. If the plants need the water, it doesn't get to the water table. They're going to use it up first, right? So the ET rate's very important for looking at the impact of climate change on groundwater recharge rates. I think in most groundwater systems, it will take a fair amount of time. There'll be a big time lag between the climate change and then the change in like the water budget for the aquifer, because the recharge rate in an aquifer tends to be quite a small fraction of the overall storage in an aquifer system. So we will see changes. We are going to see effects of climate change on recharge, and that is going to affect our water balances. Eventually, that will start to affect our groundwater discharge to surface water systems too, and we need to be understanding both the magnitude and the timing of those effects. So that's one aspect. Aspect number two, which is probably more important in the short term, climate change creates water stress in human communities as well as the ecological communities. People respond to water stress. How do they normally respond? If they've got available water that's nearby, like surface water, a dam, a rain tank, they'll use that. If they don't, if that's all gone, what are they going to do? They're going to drill. They're going to try and find water under the ground. So we see that in areas experiencing high water stress, like big droughts, there's been some big events like in California in the last, decade, where it was just next level drought caused by climate change. What happens? The groundwater usage rates skyrocket. They go right up really high because nobody's got any other water to rely on. So they drill deeper and deeper and deeper to try and get the fresh water out. So climate change has an indirect effect on groundwater because it's driving human water use patterns in ways that we've never seen before. So I think that's short term, something really to watch carefully. Longer term, it's about the hydrological process of changing the evaporation rates, the infiltration rates, and the water budget. Yeah, I hope that answered the question, and happy to talk more.
That makes totally sense. We have a dry event here in Brazil a few years ago in São Paulo region that it happens exactly what you said about the people drilling more. And because of that, we have elevated levels of contamination in the regional aquifers. Just remember what happened. It was a dry event 3-4 years ago, but it makes totally sense. It happened here in a nearby region. So we have another question. If you have the time, Professor, we know that your time is short. Okay, it's a question for Professor Gustavo. Just let me read the question. Professor Gustavo said, congratulations on the presentation. Can you present methods to be approached to fractured and porous aquifers? If there is a different approach to fractured aquifers?
Oh, fantastic question. So the short answer is yes. There are different approaches for fractured rock aquifers against porous media. And just for the audience to understand, when we talk about porous aquifer, we assume that most of the sediment or the rock has equally distributed spaces, porosity. So the groundwater flows through in like an average rate that's relatively easy to predict. We can get the conductivity of the material, and that will be representative of a large area. In fractured rock systems, the groundwater is only able to make its way through very discrete spaces, fractures and structures within the rock. And the rest of the rock bodies, there's no flow happening, right, for the groundwater. So you can imagine that the second type of aquifer is much harder to predict and model compared to the first type. For the first type, we can use standard porous flow equations. We can, monitor groundwater levels and assume that there's connectivity between point A and point B, and it's easy to measure the connection. For fractured rock aquifers, modeling is very difficult, very, very challenging, because you can't image the whole aquifer and all of its fractures and structures accurately. what a lot of modelers have been doing is just saying, if I take a very big area, all the fractures within that area will kind of average out the density of the fracture and the amount of pore space. So if I take a big area, just take the average, that will work. But that approach is quite dangerous because a lot of flow in fractured rock aquifers is actually preferential. It only is going according to the biggest of the fractures, the biggest of the structures. So modeling fractured rock aquifers is really tough. I think that field-based science using traces is a really productive and valuable way to do things. We know that we can basically work out what's going on in karst aquifer systems, that's limestone, where there's big caverns and caves and underground tunnels. We can use traces to basically identify the pathway for water to move through karst. We use things like dye, we can use temperature, we can use these isotopes I've just mentioned here. Same thing for fractured rock. The challenge is drilling those systems and getting the measuring points to intercept the groundwater in the right place. Really hard to do. But, you know, as with all challenging problems, just because it's a hard problem doesn't mean we should give up, right? We've got to keep going. Yeah, thanks for the question.
I can see that. So, Valeria, do you have a time for another question, Professor?
Yeah.
Okay, so Professor Valeria, she has another question. She said, here in Brazil, it is very common to capture groundwater. This is even seen as an advantage. What do you think about this?
Sorry, I didn't quite get the meaning of the question. Capture.
Let's see if did I mispronounce something? It's here in Brazil. We use a lot of the groundwater to supply our homes and so on. We have one of the biggest aquifers in the world, the Aquifer Guarani. So. Most of people, this is my interpretation from the Professor Valeria question. Please correct me if I'm wrong. But she sees that many people here in Brazil saw the use of groundwater as an advantage in comparison with other ways to capture water. Do you think the same? Because at least for me, I don't know about Professor Valeria, but groundwater, we see that as a more pure water, something more without not so much pollutions, something like that. So do you share this point of view?
That's a really, really great question. Sometimes it's, you know, these simple practical questions which are the most important ones, right? So, you know, using groundwater versus compared to using surface water, or using groundwater compared to rainwater, I mean, it's a huge question for us. I think it depends always on the context. A lot of my previous work, my PhD work, was actually focused in China, where there was a lot of freshwater stress. Areas like the North China Plain is very dry, massive population, huge agriculture. So the groundwater depletion in that area is very significant. Now, what we see in China is that, you know, these very densely populated areas are depending on groundwater for the fresh water supply for drinking water, because most of the surface water is polluted by like wastewater and sewage discharge and industry. So in that case, there's a reliance on the quality of groundwater, because we know that surface water is more risky and polluted. The problem that we started seeing in China was that because there's so much groundwater development, actually just the drilling of so many thousands and thousands of wells starts to create new pathways for pollutants to go from the surface to these very deep groundwater resources. They're not naturally polluted, they're good sources of water, but once we start doing lots of drilling and creating boreholes that are not perfectly sealed, or they have a long well screen, we create a new pathway for surface contaminants to reach those deep aquifers. And so indirectly, by using these safer water resources, we're actually making them unsafer by allowing the pollution. So really, really important, what I see is that drilling standards need to be very, very strong, and they need to be enforced so that we don't have a whole lot of people drilling unregulated wells that then it's all creating new pollution pathways to our deep resources. Because as I said at the beginning, a lot of these water sources, it's recharged like 10,000 or 100,000 years ago. So it needs, if we contaminate it tomorrow, we've undone 10,000 years of good work by nature and ruin that straight away. So, yeah.
All right. Thank you so much, Professor. So, team, do we have another question? I don't think Professor will have the time because
One more, and then we go.
One more question. So,
Sure.
let me check in the chat. Okay, there is one more question. Thomas asked, said, very good talk. Is there data about priority pollutions like pharmaceutical products contaminating aquifer?
Yeah, look, that's a great question. Where we're working in Australia at the moment, probably there is now a lot of focus on what we call the emerging contaminants. That's organic contaminants in groundwater. People are very concerned about compounds like PFAS because it's been released into many places, and we're only just learning about the health effects for that. Also, other pollutants that are very persistent chemicals that we can't break down using normal water treatment processes. And so I think there's been a good understanding about the more traditional contaminants, heavy metals and nutrient pollution for a long time. And now the focus is really shifting to the organic contaminants. They may be in low concentration, but they can be very harmful chemicals for human and biological systems. So that's where the focus is. I still think that it's really important to look at the more traditional pollutants as well, because some of them are really harmful. Things like lead. I mean, the level of health hazard from lead contamination in groundwater is incredibly high, like, much more than a lot of these organic pollutants. But because it's like an older contaminant, it's got less focus at the moment. So, I mean, it's always a case of weighing up the risk to health and to the environment compared to the amount of effort that you put into understanding the pollutants, right?
Yeah. Thomas also complained. I didn't read his entire question, but he also asked like or a trace like caffeine to check. Like, is there possible to organic molecules like caffeine? I know about agriculture, organic molecules, but like caffeine, like something that
Caffeine works as a tracer. The problem with caffeine is that it breaks down quickly. So if we see it, we know, okay, this is from wastewater, but often we don't see it because it was there, but it broke down into something less. So that's why we look for the persistent pollutants, because they're going to stay in the groundwater and we'll find them. So yeah, that's the approach.
Oh, makes sense. Professor, thank you so much. I think I believe there is no more room for questions. Let me check in the chat. Okay, we're going. Thank you so much for your participation. It was a very enlightening lecture.
Great.
Really, it was like very elucidative. Sorry for
Thank you. No, yeah, I get it. Yeah.
So
it's my pleasure.
I believe we can finish the lecture here, the presentation. So thank you so much. Have a nice day there in Australia.
Yeah, and have a good evening.
It's already late night. It's 9 p.m. already here in Brazil. So
yeah, okay.
Thank you so much.
Thank you for staying on and watching. Yeah.
Thanks so much. And I hope to see you in other lectures.
Please. All right, great. Thank you, everyone.
Bye-bye. Bye-bye, everyone. Have a nice evening.